I'm asked to find a power function end behavior model for this function. And really that's just kind of a fancy way of saying, what's this graph going to look like as x approaches infinity and as x approaches negative infinity? So it's a polynomial. And if you remember from pre-calculus or algebra 2, the end behavior in terms of whether the graph is going to go like up, up, or down, down, or down, up, or up, down, depends on the leading, the sign of the leading coefficient, and whether the highest power is even or the highest power is odd. So just as a little chart here, when my leading coefficient is positive and I have an even power, the graph is going to be up, up on both ends. If I have a leading coefficient that's negative with an even power, it's going to flip it upside down and it's going to be down, down. So this is like the graph of x squared, and this is like the graph of negative x squared. And as far if it's an odd power and I have a positive leading coefficient, the graph is going to look like this. It's going to be down, up, similar to the graph of x cubed. And if it's a negative leading coefficient, it's going to be up, down, up on the left, down on the right, and that's like the graph of negative x cubed. So you might want to take a little screenshot of this before I erase it. We're going to get into it a little bit more detailed right now. So I can tell by this function that if I'm just looking at up, down, or down, up type of end behavior, I have a negative leading coefficient and an odd power. So this graph is going to have this type of end behavior. It's going to have up, down end behavior. But I want it to be a little bit more precise. And when you think about a polynomial, I'm thinking about x as it approaches infinity, and I'm thinking about x as it approaches negative infinity for end behavior. So just kind of logically thinking through, as x gets bigger and bigger, x cubed is going to become much larger than x squared, or x, and certainly larger than the constant 1. Let's just take an example, like x cubed. Let's take the number 2. So 2 cubed, if x is 2, is equal to 8. But 2 squared is only 4. All right, that doesn't seem that far apart. But what about when I go, let's say, 5 cubed? Well, 5 cubed is equal to 125. But 5 squared is only equal to 25. So you can kind of see here that as my x's get larger, and they get really large as I approach infinity, this x cubed is going to be so much more influential over the ultimate y value, that is the end behavior of the graph, than this x squared, and certainly a lot more influential than the x. And I mean, 1 is just going to stay at 1. It's going to become, well, all of these terms right here, as x approaches infinity, are going to become relatively insignificant. And the only one that really matters is the highest power. That's the one that is going to determine the end behavior of this polynomial. So you can see right here, I've graphed our function, the red one here, negative 4x cubed plus x squared minus 2x. And this is what it looks like. And sure enough, it has the end behavior we had expected in terms of up-down. This is an up-down graph. Now let's overlay on that the graph of negative 4x cubed alone. And as you can see, when I'm around 0 here, it's pretty different. I mean, for one thing, the power function goes right through 0. But let's zoom out. Whoops, out. Let's zoom out. And you can see that the farther I zoom out, the more the graphs look like they're exactly the same. As x is approaching, and I don't even have to approach infinity, I'm only approaching negative 10 or negative 20 or positive 10 or positive 20, those graphs become almost entirely overlaid. Right over here around 0, you can see they're still different, but the farther I zoom out, it becomes more and more clear that that those two graphs, at the negative 4x cubed, that is the power function that is determining what the end of this graph really looks like. The way we show this algebraically is using this definition that comes right out of the book. So if this is f of x right here, this is my full f of x, I want to show that g of x, which I'm going to set equal to just my highest power here with the leading coefficient, negative 4x cubed. I want to show that this function g is in fact the end behavior model of the entire function f. And the way I do that is I take the limit as x approaches infinity, and it works the same for negative infinity, but I'll stick with that, of f of x divided by g of x, and if that equals 1, then I have proven algebraically that this is in fact the end behavior power model for this entire function. So let's do that. Okay. So I rewrote f of x. Now I'm gonna write g of x. I'm going to divide it by g of x, negative 4x cubed. And I want to take the limit as x approaches infinity of this right here. Well, I'm going to work on simplifying what's in, so I'm going to work on simplifying this function a little bit. What I'm going to do is I'm going to say, okay, I want the limit as x approaches infinity of negative 4x cubed divided by negative 4x cubed plus x squared divided by negative 4x cubed. All I'm doing here is I'm separating out the common denominator, making it separate little terms, minus 2x divided by negative 4x cubed minus 1 divided by negative 4x cubed. And I know we could change that into, now since we're using the properties of limits, into the limit as x approaches infinity of each term individually. So I've written all those out in an instant there, you didn't even see me do it. And let's look at them one at a time. Well, it's pretty clear to me that something divided by itself is 1. Let's look at this one here, and this is the one really that we're going to focus on because these other two are going to work just about the same. If I take this function right here, x squared minus divided by negative 4x cubed, I would have x squared over negative 4x cubed. And I can see that I can simplify that into being 1 over negative 4x. Well, what's happening to this 1 over negative 4x as x approaches infinity? Well, as x approaches infinity, this number here, this x, is getting humongous. I'm multiplying it by negative 4, so this term right under here, my denominator, is getting really, 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 really big. So if I divide 1 by something huge, my limit is going to approach 0. Because, 1 gazillionth, 1 gazillion gazillionth, I mean, the larger this number gets, and infinity is pretty large, the smaller this whole term gets, so it approaches 0. And you can see that that's going to be true for this, and it's going to be true for this, and it's going to be true for this. All the other terms are going to approach 0 as x approaches infinity, so the only one that I'm really going to be concerned about is this one here. Well, what is the limit as x approaches infinity of 1? Well, the limit of a constant is 1. And what the rule says, I go back up to the top here, the definition says, right end behavior, because I was dealing with x approaches infinity, if I take f of x divided by g of x, it's going to equal 1. So it's a way of proving using limits that really the end behavior is determined by the leading term when the polynomial is put into standard form.